Welcome everybody. Thank you so much for attending Professor Ghani's talk, despite this being election day and it being a exciting slash nervous time for everybody. But I really appreciate all of you being here. We are very fortunate to have Professor Rayid Ghani from CMU here with us to uh, talk about his research. Welcome, Professor Ghani. I'm going to introduce him and then he's going to start his talk. As always, if there are questions, you can use the chat window to let me know of your questions, and then I can ask Professor Ghani. And then, we'll have a 10-minute Q&A session after his talk. Uh, so Dr. Rayid Ghani is a distinguished career professor in the machine learning department and the Heinz College of Information Systems and Public Policy at Carnegie Mellon University. Rayid is a reformed computer scientist and wannabe social scientist focused on the use of large-scale AI machine learning data science in solving critical public policy and social challenges in a fair and equitable manner. Among other areas, Rayid works with governments and nonprofits in policy areas such as health, criminal justice, education, public safety, economic development, and urban infrastructure. Rayid is also passionate about teaching practical data science and started the Data Science for Social Good Fellowship at the University of Chicago. Before joining Carnegie Mellon, as I just said, Rayid was the founding director for the Center for Data Science and Public Policy and a senior fellow at the Harris School of Public Policy at the University of Chicago. Rayid has also served as the chief scientist of the Obama 2012 election campaign, where he focused on data analytics and technology to target and influence voters, donors, and volunteers. Thank you so much, Professor Ghani, for being here with us, and we look forward to your talk. You can get started whenever you are ready.
Sounds good. Thank you. And thanks for having me here. I keep moving closer and closer to Pennsylvania, and then unfortunately I can't physically visit, but hopefully I'll get to. I've never actually been to Penn State, so it'll be good to visit someday when this is all over. And yeah, I'm surprised. I guess the relief of Pennsylvania crossing the line makes it more likely for people to show up. Otherwise, we're all refreshing our windows or our scraping web scraping scripts, whichever one you're using. Yeah, so I thought what I could do is, we can have a separate conversation about elections someday. But I thought what I could do is talk. I mean, let me share my screen. Talk through some examples of kind of projects that we've been working on over the last few years, but we really think of them more from the angle of not just doing, a lot of us, from different departments and different disciplines are sort of trying to use data in different ways to do something good. And we can sort of have arguments about what that good means and how good is it. But I'm kind of focusing on a specific dimension of good. Again, a lot of these projects that are kind of social impact or social good projects, arguably one of the goals we want to have in all of these projects is equity and fairness, and thinking about how do we treat them as primary goals rather than nice to have. So what I'm going to do is some of you might be familiar with some of these projects, but I'll kind of go over some recent projects that we've been doing, and then kind of step back a little bit. So the first one I want to talk through is a project we actually started a few years ago in Kansas, and this is the initial project idea was, we all know the criminal justice system here is totally broken, and these are just numbers for jails, right? These are not prisons. These are just local, county, city jails. 11 million people going through. The depressing parts are kind of the 2/3 of them people going through have mental health issues and substance abuse disorders. So this county in Kansas called Johnson County came to us and said, look, we also have a high recidivism rate. People keep cycling through the system. And we think a lot of the root causes are really around mental health needs. They have mental health needs that they're unmet. And so we want to do a trial program where we have resources to go and do proactive outreach to a couple of hundred people a month, and provide them with mental health services with the goal of reducing recidivism. And they wanted help in trying to figure out how do we allocate those resources, how do we pick those people. And so step one, that was kind of, the usual, do we even have the data to be able to do this? And working with them to get access to mental health data and criminal justice data from jails, from police, other help data from emergency rooms. And because a lot of these people often visit emergency rooms, data around their housing, homelessness, things like that, and trying to combine that to see, do we know enough about each person? And second step was, can we identify people who are at risk of recidivism? The third step was trying to figure out, how do we identify mental health needs? And then once we've done all of that, so at the beginning, can we be efficient enough in identifying people who are at risk of recidivism? So treating it like a more standard prediction problem, and saying, okay, we could accurately do this. Now the real question comes. The prediction was the easy part. Is, can we actually reduce their risk of recidivism? So a year and a half ago in June, we started a randomized trial with them where we would generate a list of a couple of hundred people, high risk. We randomized that, and then they intervened every month with those people through mental health outreach programs. And so over the last year and a few months, they've been every month going out and doing these interventions. And then we're getting that data back. So we have some early data back, but it's because we're looking at 1 year recidivism outcomes, hopefully we're going to be getting data, by next June, that 1 year outcome back, with the caveats of COVID. And so one of the things that happened was they stopped arresting people, which is great. But that reduces the power of our experiment, because now already we were sort of limited in number of people they could intervene on, and so now we'll see if we can still detect any differences based on a control group. So basically the idea here was, how do we couple the prediction piece, which from machine learning side we know how to do, with the intervention piece, and design these trials so that we can measure effectiveness of these types of, for two types of things. One is, does this program even work? Does it, reduce recidivism rates? But then more importantly, are there any sort of heterogeneous treatment effects, for example, where we find it works well for certain people, but doesn't work for other people. So then we can design new interventions for people that it's not working for. So that's kind of an ongoing project. Some of the older ones that this is a really old one, but where we started a while ago, it's still ongoing in Chicago with detecting kids with lead poisoning, where most cities today, Chicago being one of them, but also I live in Pittsburgh right now, and same thing is they are reactive to to how they deal with lead poisoning. They wait until somebody gets lead poisoning and then send inspectors to check for lead hazards in the home. And if they find them, which they usually do, because how else would a kid get lead poisoning? They then try to remove those hazards. And the problem is these effects are not reversible. Once you've been exposed to lead and have these effects, horrible things, you can't really do much about them. And so the idea there was, can we again identify kids at risk of lead poisoning before they get lead poisoning? So typically the lead poisoning happens at, when kids start crawling and picking up lead dust. So it's about 9 to 12 months. And so if we can detect early enough, between birth and maybe a couple of months old, that gives the health department enough time to detect those hazards, do inspections, and then remediate and remove all sources of lead before the kid is able to walk. And so again, we ran a trial over the last couple of years where, again, based on these predictions, sent inspectors to check for lead hazards, and then got data on blood lead levels in the future to find that we can actually find a higher proportion of lead hazards compared to what they were doing before. And so that system is now deployed in Chicago in both the health department, but also in a hospital system to help do this even earlier. So when a pregnant woman goes in for a checkup, the system can ideally it raises a flag saying the kid that's going to be born is going to be high risk of lead poisoning. So the health department has even more time to prepare and plan for these things. This is, again, unfortunately, an ongoing project, which is reducing all the horrible things that police officers do, unfortunately, too often. Unjustified use of force, unjustified shootings, all of those things. So this is some work we started, again, a few years ago with the Obama White House, working with a few police departments to identify how do we, so it turns out most police departments actually have these types of systems in place that they're called early intervention systems. And the goal of these systems in these departments is to raise flags when an officer is going to be at risk of doing something bad. It turns out nobody had, they'd all bought them, installed them, but then nobody had bothered to kind of evaluate or even see, how should we evaluate them? So they just were using them. And turns out when we worked with these departments, looked at the data, they were mostly useless. So our first project was with Charlotte Mecklenburg in North Carolina, where we found that the system they had was flagging more than half the police officers, which makes it completely useless. Nobody trusted it. And even while doing that, it was missing about half the officers who were going to go on to do something, right? So basically, you're flagging slightly. Slightly, actually it was flagging half the officers and missing slightly under half, right? So basically random, slightly better than random. And so the reason for that was that the way they'd built it was they decided, a few different thresholds, right? A lot of these systems get built that way. And then where they say, oh, if you have, more than 3 complaints against you in the last 90 days, raise a flag. If you have 6 uses of force in the last 6 months, raise a flag. And while those might be correlated, they're not really signals of any early warning, right? They're signs of late warning, basically. You've already done these things at that point. One, it's sort of not contextual, but 2, it doesn't really help you prevent. It doesn't help you do sort of preventative interventions. It doesn't help you fix things. It just helps you, at that point, all you can do is sort of get rid of the officer because it's too late. So we worked with a couple of departments in Charlotte to get their data, to kind of get everything from their HR history to dispatches to stops and arrests and complaints and investigations, and use that to build a system that ideally, again, identifies early. And the way they were looking at it was they wanted the timing they were looking at it, that we need about a year to work with an officer to try to fix things, to try to do preventative programs, try to do training. So the system we're building would sort of identify these incidents a year in advance in order to prioritize which officers they try to intervene with. And it was interesting because the type of predictors we found, they're the usual ones that you would expect, which was history of these types of things. But then there were things that make sense in hindsight, such as sort of repeated dispatches to domestic abuse cases or repeated dispatches to suicide attempts, especially involving, let's say, kids, that made these officers temporarily sort of high risk in the near future. And some of those are sort of stress indicators, and some of those potentially could be dealt with by providing a cool down period or not dispatching them to those things, or connecting them with other mental health resources or training programs. And so, for example, Charlotte, ended up hiring a counselor to sort of deal with some of these issues preventatively. So that system has been deployed there now, and we're sort of getting now that data back to also evaluate and see the effectiveness of this type of system. And then, then there's a whole class of projects that we've been working on the last few years around sort of designing sort of more effective inspection type programs, right? So inspections kind of happen in different places in different governments, whether it's workplace safety or housing safety or waste disposal compliance, with when for example, this, EPA has these regulations around what the waste, how you should dispose of hazardous waste, and there are 400 and something thousand facilities in the country, and they only have resources to inspect a few thousand of them every year. So how do you prioritize those? And the interesting piece there comes from framing it as, depending on what you care about, if you just want to deal with it as an efficient solution, what you can do is say, I have 4,000 inspections. I want to maximize the number of violations I find. And while that might be okay, that's not your goal with this inspection program, because the goal of these inspection programs is typically deterrence, right? Reducing the number of actual problems rather than detecting problems. So you could have a system that does 4,000 inspections and finds 4,000 problems, and it turns out there's a problem everywhere. So that's useless, versus a program that finds 0 problem but deters everybody else is a more effective program. So how do we design these programs that are not just purely efficiency? And similar to, there's another example, which is work in New York on New York City created this team called Public Engagement Unit. With one of their goals was to go out and proactively do outreach to tenants who might be at risk of harassment from landlords, right? If they're living in rent subsidized units, increasing their rent, trying to evict them when they might not know of their rights. So they had resources to go out and proactively connect people with legal resources, but they couldn't do it for everyone right away. They kind of had to figure out, who do we prioritize? Who do we go to first? How do we rank them? And to work with them to help them figure out who are the people at risk, and then prioritize those people as they go through these. Another example is, water pipe breaking, which is again a more common issue than a lot of us probably get exposed to. So this is some work in Syracuse, New York, where they get a break every other day in the city, and yes, it's costly to repair, but it's also affects people because you don't have water, and also affects your ability to, most of the times when there's a water break in an area, grocery stores sort of stop selling any, they have to shut down their refrigeration units, and they can't sell anything. So for certain areas, that's a bigger deal, in addition to, the cost of repairs and things like that. So we work with them to help them kind of see, can we actually predict the risk of a pipe breaking? And what was interesting here was, like, unlike some of the other projects where if you can predict a pipe is likely to break, let's say in the next couple of years, the intervention here is not dig up the street and fix it, because that might be too expensive, because you're going to be wrong a lot of the time. What they wanted to do with these predicted risk scores was to coordinate with the roadworks people to figure out, if you're really high risk and a road is going to be dug up anyway, well, let's go a little bit deeper and fix these pipes. If it's sort of medium risk, can we prioritize that for putting in sensors so that they can detect breaks before they get bigger? And so it was sort of a more nuanced intervention where it's not just trying to fix it, but it's really more trying to instrument some of these and spend some more money in a more targeted way. And then I think the last example is, again, a little bit different. This is some work in Jakarta where, we sort of often talk about traffic accidents, and yes, traffic accidents happen in every country, and yes, they happen in the US as well, but it's nowhere as close to drastic as, in a place like Jakarta, where a few thousand people die every year from traffic accidents. And like, a lot of these smart cities, one of the things they did was like, oh, maybe we can figure out what's going on by putting in cameras. So they put in 5,000 cameras. And then again, as you would expect, they realize we don't really know what to do with the video coming back from 5,000 cameras. And so what they really wanted to understand was, what were the root causes of these accidents? The idea wasn't to predict an accident, because if you predict 10 seconds earlier an accident is going to happen, what are you going to do about it? So it was really, the intervention here was, if we can figure out what are the root causes, can we change, whether it's certain policies are not implemented, they're not being enforced, or other safety regulations. So it was really more about understanding what types of things lead to accidents. And the idea was not to sort of automate that, but be able to give their analysts the data. So they were asking whether, oh, we don't have data to tell us what's happening, but we have these videos. And so the idea was like, can we detect events like these that could be leading indicators of accidents, right? So non-vehicles using, so food carts, for example, or motorcycles that are overloaded, or pedestrians kind of crossing through traffic, or cars going the wrong way. And the interesting piece here was that there's a lot of work, pre-built systems, pre-built models that exist for a lot of object detection things, right? But there is no category for food carts. There's no category for motorcycles in in the US and Europe. Look very different than motorcycles in most of Asia. They're being used to transport cargo, and there is no category for that. Even if you sort of look at simple things like buses, the generic bus model doesn't work for buses in London because they look very different. So a lot of it was really sort of how do we do transfer transfer the models from designed for US to design for the rest of the world, and then using it to sort of detect things like what types of objects are moving in what direction, where, and then finding, and then finding kind of creating structured data that analysts could use to find things like this, right? So they found sort of this was one factor that kept coming up, and this is a two-way street, right? So we kept finding sort of this repeatedly, cars coming in the wrong direction, and in this case, the policy, if this is leading to accidents, right outside this frame, then putting in a median in the middle, a block in the middle, would stop the cars from going over, and that could be a way of intervention they would take. So in some of these cases, the answer wasn't automate the whole thing, but it's really providing some of these structured data feeds to their teams. And so kind of thinking about this as in a lot of these projects, right, that we're kind of doing three things, right? Where, let's say in the case of the recidivism and mental health outreach, right, we're trying to understand sort of what are the factors that lead people to recidivism. We're then trying to figure out which individuals are going to be high risk of recidivism, so we can focus our resources. But then we're then trying to change their behavior. We're kind of then say, okay, now the goal is to reduce their risk of, we don't want to just understand, we don't want to just predict, we actually want to change their behavior and reduce their risk of recidivism. And so a lot of this work is really combining things from traditional statistics and machine learning and social sciences to see how do we build it in a system that's resulting in reduced recidivism. And so if we sort of think about that, they're kind of all across all of those problems, there were sort of three common themes. Right? One is that none of those are autonomous systems, right? They're all collaborative systems where if machine learning, AI, and none of those things existed, the humans would still be doing what they're doing. They're not going to stop helping people from going to jail, or from graduating high school, or from getting lead poisoning, or from reducing these incidents, or making housing safer, right? So it's primarily a human process, and our systems are kind of helping make that hopefully better. So they're kind of none of them are making any autonomous decisions. They're helping a person do something. Second is, and this is unfortunate, but in all of these problems, we have limited resources. We can only, the organizations we're working with can only intervene with X% of the people that they're supposed to serve. And that X is often, under 20, 25%, right? It's sort of 1%, 5%. In the police case, it's 10%. In the lead poisoning case, it's also about 10%. In the case of the recidivism mental health resources, it's a couple of hundred people a month, right? So in all these cases, we have limited resources that we have to allocate through these systems, which sort of leads to the third point of conflicting policy goals sometimes, right? So because of limited resources, we want, the framing that a lot of these organizations start with, a lot of the government agencies, is we want to make sure we make the most efficient use of the resources we have. you sort of have to question that and say, well, no, that's not your job. Your job as a government agency is not to make the most efficient use of resources. Your job is to make the most equitable use of resources. And efficiency is not the only goal. But often sort of you want to, the goals are, you want to make sure that everybody who needs the help is getting this type of help. You want to make sure that you're preventing the bad outcomes, but you want to make sure that you're doing it in a way that's efficient as well. And so the question is, how do you design systems that are supporting these human decisions to allocate limited resources in a way that's fair and equitable and balancing all these goals? And that's sort of the running theme across all of these, is how do we develop these collaborative systems to make decisions that lead to fair and equitable outcomes? And so if we sort of start thinking about that, focusing on kind of the fair and equitable outcomes is often when we sort of think about, there's a lot of work that's been going on the last few years on machine learning and fairness, right? And a few things to sort of keep in mind there is some of it comes across as, machine learning just discovered a thing called fairness, and we should do something about it. And well, there's been hundreds of years of work in different fields that have been doing something about it. So it's not a machine learning problem; it's a societal problem. But then I think the other thing that we sometimes in the machine learning field sort of forget is our whole focus becomes, how do we make this machine learning model fair? And I often sort of talk about, like, what's the point? Who cares if the model is fair, right? So if one of the examples is if we look at sort of the example, so the thing I was talking about with the lead poisoning case, in that case, what ends up happening is that what the machine learning model does is predicts which kids are at high risk of lead poisoning. If I make that system fair, and for now, let's ignore the definition of fair, let's assume that we agree on that definition. The next step is then the health department has to call the people who are the parents of those children and make an appointment for a lead hazard inspector to go and inspect their house. And so the default approach was, well, we make this model, we get this high risk list, and we call them, and the calls were being made in English. And so the perfect model, perfectly fair model, now leads to people who don't speak English getting left behind, not getting inspections, getting lead poisoning, right? So that's kind of it's a real but kind of an obvious example. But the idea is that, we don't want to kind of get stuck with making the machine learning system model fair. We want to sort of think about the overall system and the overall outcomes fair, and make sure that we achieve that, right? So this is kind of the high level view of, well, we want to kind of first figure out, how do we even define what we mean by fairness or equity? Because that's unclear. Who decides that? How do we decide it? How do we sort of agree on those societal values? Second is, how do we actually measure that and detect different types of biases? How do we discover or understand what the root causes are? Is it the person developing it that's the problem, who screwed up? Or is it the person taking action on it? Or is it the data? Or is it our machine learning models? And then once we get understanding it, how do we improve the bias there? And knowing that we're never going to be able to make these systems, make these models, make these outcomes perfectly fair, what is our approach to mitigating the impact of these unfair? Because we can't fix it all with the machine learning stuff. We're going to have to we're going to have to create interventions and actions that can mitigate the impact, the use of these types of models that are going to be unfair. And then how do we set up a monitoring and evaluation system that sort of, just because we made something fair today doesn't mean it's going to be fair tomorrow. And so that's kind of the overall, is starting with the definition to measuring to understanding to improving to mitigating and monitoring. And I'm going to kind of go through some of these things little bit deeper, right? So in terms of kind of thinking about where some of these biases come from, right? We sometimes kind of go in different dimensions. Sometimes we'll sort of talk about, well, this machine learning system is biased. Like, no, typically it's the people who are building it caused that problem. The system itself doesn't have much it does pretty much what we tell it to do. But if we think about all of these things, we've got the world, and that's probably the biggest problem, is the world happens to be racist and sexist and bias. And so anything that gets generated as a result of that world is going to have problems. But then, I'm hoping there are at least some social science people here, right? It's like, this should look very familiar. This is not a thing machine learning talks about or thinks about or does anything about. Like, well, data, my matrix is so perfect that whatever I do with it is going to be, great. But there's going to be data is going to have lots and lots and lots of biases. So the one that's we kind of know how to deal with things like sample biases, right? We can at least, although I'm saying it at the wrong time, given that all the polling results we're looking at right now, they don't know how to deal with sample biases, and clearly they don't know how to deal with measurement biases either. The one that I find really, really, really difficult to deal with is sort of this label or outcome bias, right? Because we sort of assume, like the example from the projects I was giving, the project with police departments on identifying officers who are going to go on and do horrible things. The label in that case is, so every time any police officer uses force of any type, or discharges a weapon, or has an injury, or has an accident, that incident gets reported. It has to get reported. And then it gets investigated in internal affairs. And they internally label that as justified, unjustified. So that's the process. Now, and that becomes, so what we want to do is not predict that they're going to have an accident. We're going to have, because that could just be happening as part of their natural, or they'll have, sometimes they might have to use force. Ideally, we live in a world where they're not doing it, but sometimes it's going to happen. And so every use is not unjustified. And so for these machine learning models, the label is unjustified. But that is coming from this process that the police department has to investigate these incidents and then decide justified, unjustified. Well, if that process is totally corrupt, and then they're going to say everything is justified. And, I used to live in Chicago. That's one department that's totally corrupt, and will say everything is justified, right? So you will never predict anything is unjustified. But if you don't go to that extreme, there's going to be a lot of errors, and we can't easily look at them and say, oh, I'm going to reverse this label because I don't think this should have been justified, because that requires going back to that world, reopening that case and saying, okay, knowing what you know now, was this justified? That's going to be really, really hard to do. So that bias is the one that's very, very, very difficult to deal with. Or to take other things, like when we're predicting things like somebody who needs extra support to graduate high school on time, the label is that they graduate or not graduate. Well, it's not something inherent about the student that makes them likely to graduate or not graduate. It's maybe the school didn't have the support structure that these students needed. And so we're not labeling the student, we're labeling the student in this environment under the circumstances didn't graduate on time. And so now if we sort of apply it to the future, a lot of these things get really tricky in kind of dealing with this, right? So that's a big issue here when we're dealing with bias, because it doesn't happen uniformly randomly. It's not noisy for everyone. It's going to be biased in very specific ways. So there are a lot of issues here about where bias in the overall system comes from. Then sort of this is the part that where a lot of focus happens, right? Is when we're the machine learning pipeline can be a cause of a lot of these biases, and then the biggest bias is sort of people like us, who sort of make choices in that pipeline about what to do, about what data sources to use. So somebody, this happens all the time, where, with students in actually real work situations, where somebody will say, oh, I decided not to use that data source because I think it wasn't accurate. That's just a choice that we made. We didn't really know. It's a design choice. Or, oh, I decided not to use the race variable because I think that would make my model racist. Well, do you know that? Maybe it will help you build a better model. You'll help the people you're trying to actually help more effectively. So we often make these choices as developers of these systems that could lead to bias. Second thing is we also have a lot of design choices we make. So and I'll go into a little bit of that a little bit later. But then the last sort of piece of bias here comes from my example of where the phone calls in Spanish or in English come from, right? Is it's not the bias in the world or the data or the machine learning pipeline, it's how we use those to intervene. If the interventions are happening through phone calls in English, if the interventions are happening through phone calls, period, people who are not reachable from phone calls, you're not going to be able, you're going to create a bias right there. Or if your interventions are all in person, then people who have access to that are going to have more, more. So I'll come back to some of the questions that are coming up. So kind of going a little bit deeper into the, a couple of examples on where sort of this ML pipeline bias that I see come all the time is, if you sort of think of this as, here's a system we're building, right? We're going to get a bunch of data, we'll link them together and we'll process it, we'll do some exploration, build some models, do some model selection, deploy it, test it, maintain it, all that kind of stuff. Well, even from the beginning, the choice of data sources, but even sort of something as what we think as trivial as like record linkage, right? When we're linking record together, we're making these decisions about these two records are about the same person and these two are not about the same person. Well, let's say we're doing this linkage on, people records, and we find that, people with long names with lots of consonants next to each other tend to have more typos and we're going to miss them. Or people with common names might get linked together when they're not the same people. And so if we look at sort of the downstream impact of that, we're either adding information to people that's not about them, or we're missing information about them. And that is not, again, happening uniformly at random. It's happening disproportionately to certain types of people. And so keeping that in mind up here, like we sort of make a decision here and then we move on. But if we've stored sort of this decision that we made and looked at its impact on bias downstream, we are able to actually think through, well, what are we doing here? What's the impact of that? Same for like really simple things like imputation, where we often just do some imputation. Well, imagine a data set that has, 80% male and 20% female, and we're missing some attribute about some females. And if we just do some mean imputation, we've now just made all the women look more like men in our data. And that's going to affect the predictions we make about them. So like very simple, obvious things that we don't think about when we're doing them have downstream impact on biases that get introduced and are often hard to change once you're sort of all the way down, right? So once we've kind of looked at some of these things, the next step sort of becomes like, how do we even define what bias is, right? And this is sort of, there's a whole set of metrics that the machine learning literature has, again, that's sort of discovering these things when they've kind of existed, some in the legal world and some just in the common sense world for a long time. But generally sort of the idea has been, do you want to be fair in terms of allocation of resources? Do you want to give equal amounts of resources to different people, or proportional? Or do you want to be fair in terms of the types of mistakes your system is making on different types of people, right? So like, for example, the false discovery rate will be, if it's basically your depending on who you are, looking at of all the people that you predicted as ones, also people, how many did you miss, right? Or false omission rate. And the idea is that there's a lot of papers on what these metrics are, and more importantly, papers on sort of, if you care about this, then you can't get this. So a lot of these impossibility papers that are all useful. What they sort of lead to is, one, they're kind of if you ask somebody, so the types of systems examples I was giving, if you ask any of those policymakers or people who are using those systems, which metric do you care about? You're going to get blank looks. The other thing that happens when you ask people, when people read sort of some of these things, the conclusion they reach is, oh shit, I read this paper, and the paper basically said that you can't get fairness because if you want this, then you can't get this, and if you want this, you can't get this. So I'm thinking I shouldn't be using any of these tools, any of these statistical machine learning tools to do any of this. Well, that means that today the process that you're using with humans is so perfect that humans are so fair, they're making perfect decisions, there's no racism, there's no sexism. So using these things would just make that process worse, right? Like that's not where we want to get to. So one of the things that we ended up building was sort of we call it a fairness tree. It's fairly straightforward. I mean, kind of zoom into something. It's sort of helping policymakers go from what they care about, what they're doing, to what metrics they should care about. So rather than kind of starting with these mathematical metrics saying, okay, and so here's a zoomed in version of one piece of it. Like, okay, are your interventions punitive or assisted, right? So if you're doing horrible things like keeping people in jail or not giving them bail or doing predictive policing, which arguably you shouldn't be doing in the first place with these types of tools, then a false positive is much, much, much worse than a false negative, right? Because you're going to be hurting people. And so a disproportionate false positive rate is much worse than a disproportionate false negative rate. So focus on sort of, and depending on sort of a bunch of these things, you want to be on this side, right? So think about, but if you're sort of trying to help people to provide them with resources for, preventing lead poisoning, and often you're sort of in this world of you can only help a small fraction of the people who have the need, then you care about recall parity. But if you can help a lot of people, then you might care about these. So the idea was really to go from the program that you're running, the interventions that you have, and the setup you have to these types of metrics, so that you can start, as you work with consultants, researchers, vendors, you can kind of give them, I'm assuming if you're at all familiar with any of sort of fairness type work, you've all heard about the Compass ProPublica things that happened, right? The problem there was not that the system was biased or unbiased. The whole, for me, the more interesting part was, ProPublica said that the system was biased. The company that built it said, no, it wasn't biased. It was fair, but we were using a different metric. And so the argument was not about fairness or unfairness. It was about which metric. And the people who were asking for that tool had no idea about any of that, did not define what metrics should have been used, could not validate the system was actually achieving that metric. And it was just a total mess. And so that's kind of the idea behind this, was that it doesn't matter what you do, think about what metric you care about, and then you can give that out as a requirement to people that you're working with so that they can build for it. You can make that, disclose that publicly, this is what you care about, and then you can evaluate and measure those types of things. And so one of the things we built a couple of years back was sort of this simple tool that kind of goes from, once you figured out what metric, then you can take and just audit what the bias is in your system. And again, all it does is really just looks at all the confusion matrix metrics for each group that you care about, measures that and says, you have a bias for Black people in false positive rate, and you have a bias in, women on false emission rate. So it's really, again, for the same kind of policy use cases of, before you use a model, you should audit it, put the audit report, make it public, and show that it's not biased before you start using these types of things. The second use case, so this is kind of the end audit use case. Second use case is really for people like us who are building these types of systems, right? So most commonly we'll sort of define some performance metric, and we'll sort of, build a bunch of models and pick this one, the orange one in the beginning, right? And the idea here is like, well, yes, but there is this other much more important dimension that exists. And if you look at that, then you at least start making somewhat more informed choices, where you might still use the orange one, but maybe you should be using this green one, because it might be worth looking at, some of these trade-offs. And the other thing is that we have some results that we sort of, there's a lot of talks I attend on this topic. There is kind of this implied, there's a trade-off between accuracy and fairness, or bias of some sort. And actually, there is very little, if any, empirical evidence that trade-off exists on real problems. Because most of the work that's happening, it's either theoretical or tested on mostly sort of toy data sets, right? So the most common one might be Compass, which we don't actually have the whole data set. We have a handful of attributes, or the useless adult data set, which has like a subsample of this census data, or this other credit data set, which has, again, like 5 attributes, right? No real data set has 5 features. And so a lot of those those claims have been mostly theoretical, and I'm not going to talk about it here too detailed, but we just actually did the study where we looked at a lot of these projects that we just talked about, and actually, designed sort of this algorithm to get this to kind of take an existing set of predictions and kind of do these corrections. And we found that in all of the examples I gave, we found very little evidence for any trade-offs. We found that we could reduce the bias to pretty much to get to parity without any reduction in accuracy. It's, again, very specific to the class of problems where we have limited resources and benefit allocation type things. But even for those class of problems, finding that there is no trade-off, that we can get both accuracy and fairness, for us, that's a huge sort of, we were shocked that was actually the case. So, but that's kind of very new, recent work that we can talk about at some point. Anyway, so this is kind of the intuition, right? And so here's what it looks like on a real project. And this is a project around recidivism, where we're looking at, again, the risk of recidivism. And the x-axis is, for now I'm just saying accuracy-based metrics that do precision or predict, positive predictive value at the top 5%. And the top y-axis is gender false discovery rate disparity, right? So the ratio of false discovery rate on female versus male. And here we find that, this is just a grid of a bunch of models. And we find here is that, you might have picked this model, but at least between these two, it's obvious which one you would pick, but you can also pick this one here, right? If you want to, in this case, we are seeing some trade-off, right? But if you look at a different bias metric, which would be the opposite, so depending on your intervention, we find that trade-off, now it's not as clear, so you're going to have to trade off things here. If you want to reduce bias and get the parity to 1, you're going to have to give up a bunch, right? So just kind of thinking through some of these things, having these tools in the workflow helps you at least think about, oh, I don't have a single dimensional problem. I have to kind of think about these things. I'll give you sort of one last actually, yeah, I'll go through this for a couple of minutes, and then, because we have a few minutes. So this is a project that we're doing with a hospital system on type 2 diabetes. And the idea was, it turns out actually there are these guidelines that you have to follow before you test somebody for diabetes in order to get reimbursed, right? So it's this US Preventative Services Task Force that has these guidelines. If you meet these guidelines, then your hospital, then your insurance company reimburses you for that test. Otherwise, the hospital doesn't get reimbursed. Turns out, just like everything else, those guidelines were designed based on data from white people. So they're very, very accurate for that. But for non-white people, they weren't extremely accurate. So this hospital system in Chicago were mostly serving kind of Asians and Hispanic that have a higher diabetes rate. And they wanted to say, well, can we develop a better system for doing diagnosis? And they wanted, in this case, they're looking at 3-year diagnosis, because lifestyle change in behavior is going to take about 3 years for them to do. It's not, you press a button and people's lifestyle changes and you don't have diabetes, you don't have a risk of diabetes. So here's kind of what we, ignore all of that stuff. Here was their existing practice. Here's what they were doing before using any machine learning. So doctors were using their experience to say, this person might be a risk, so I'm going to screen them. And so we measured their false emission rate, because again, it's an assistive intervention, so we don't want to miss people disproportionately. And so it turns out that for their false emission rate was much higher for older people, 40 to 70, 40 plus basically, compared to younger people. It was much, much higher for, again, Native Hawaiian and Native American than a lot of other, and it was about the same for, so that the existing process was biased, just, wonderful human decision-making. And so then we said, okay, let's build the most accurate system. And so this was, the blue is the most accurate overall, globally accurate, regardless of fairness for now. And the blue one, if you notice here, the blue is lower than the orange for every single subgroup, right? So it's better for everyone. It's better for male, better for female, better for white, better for Native American, everyone. But the blue one has more disparities, right? So the orange one before was equally bad for both 40 to 70 and 70 plus. But the blue one is much worse for 70 plus than 40 to 70. And so now first that's sort of a societal choice for these types of things. Like, what do we care about? Do we care about reducing diabetes for everyone, or do we want to also reduce the disparity in diabetes for people, right? Because the orange system is fair for these two, but it's probably sort of unjust, right? Like, it is too high. The blue one is unfair towards 70 plus people, but it's better for them. It's better for both, right? So again, this is not a choice that I should be making, and it's not a choice that the doctor should be making. It should be, the people being affected by it, the policymakers. It has to be sort of some sort of collaborative decision-making process. As what do we care about, right? So then we started thinking about, okay, how do we actually, what if we wanted to optimize for certain things, right? So let's say we wanted to make sure what's the lowest rate we can get for Hispanics. And so when we tune a system to get kind of the lowest, that's kind of the light blue, right? So the best Hispanic one, it's slightly lower over here, but in order to do that, it increases the rate for 40 to 70, and it increases the rate for Native Hawaiian. And so then, we can sort of say, well, what if we want to build one that's fair across different races? So this mustard colored one is kind of about the same for every race. But in order to do that, it had to make it worse, right? So it kind of gets complicated as you're trying to kind of both figure out the values of the system and then implement it technically. And so we started taking a different approach, right? Which was, this is work that we were doing with Los Angeles on reducing misdemeanor recidivism. And so the idea was that this city attorney's office had built a new team. And what their goal was, they were all these people who kind of keep getting arrested for misdemeanors. They go in front of a judge, and LA's jails are full. And so basically, if anybody who gets sort of sentenced to, fewer than a few months, basically just pleads out. So they go in, and the judge sort of releases them. They get arrested again 3 days later, go back in, keep going through this cycle again and again, and it makes things worse. So what their team their job was to say, okay, how do we actually help these people? How do we connect them to services that they need, different diversion programs, different social services? And with the bottleneck they had was that typically when the police would arrest somebody for misdemeanor and take them to court, the city attorney's office had about an hour or so to show up to court and plead their case. And they said, look, in an hour, we can't even pull all the data together about these people, let alone make these connections, figure out what service they need, make sure there's space in that program. And so they asked us for help in what's going to initially sound pretty horrible. Like, oh, can you help us figure out who's going to be coming back? Who's going to be getting arrested in the next month? And what we want to do with it is just prepare their case file, make connections to which programs they need to be enrolled in, make sure that there is space, and we can kind of keep this file there, literally actually a paper file. And if they get arrested and show up, then we can take this file and go to court and plead this case and connect them to these services. If they don't get arrested, then nothing happens. This file just stays there. And so first thing we have to make sure is make sure, like, what are you going to do with this list? Who gets it? Does the police ever get access to it? Who else gets access to it? What is it used for, both legally and contractually? The second thing was to say, okay, well, how do we actually build such a system, right? So when we started building this, the first version that we ended up building was, again, sort of this default, let's build the most accurate system. In this case, they had capacity to help to prepare these files for 150 people a month. And so the most accurate system will be basically, the metric would be, PPV or precision at the top 150 people in our list. And so the one that the highest precision is the one that you prepared case files for these 150 people. And the more you got right, the more who came back to court, the more efficient you are. And so that was sort of our first version, right? So, okay, the first one was about 73% precision at the top 150, 103% efficient. But here's the thing about this one is, if you look at the current status in LA, the recidivism rate for Hispanic people was much higher than the recidivism rate for white people. And this most efficient system had a much higher accuracy or precision for white people than Hispanic, right? So in this case, it was better for white people than for Hispanic, but Hispanic people had a higher recidivism rate. And so if you use this system, here's what happens. Over time, you help both white and Hispanic groups, but you help more white people. And so this disparity that you have increases over time. So your recidivism rate disparity goes up if you build this system. So then we gave them option number 2. So option number 2 is going to be equally accurate for both. It's going to cost additional 2% in efficiency or precision. It's going to be 2% worse. And so here's what happens if you use that system. It's equally accurate for both. So both of them reduce their recidivism rate. Both of them reduce equally. So that's optimizing for equality, right? It's sort of saying, I'm going to keep the status quo disparity and keep that constant throughout the next few years. And that's going to cost you 2% additional. And we gave them option number 3, which is optimizing for equity, which is more accurate for Hispanic people, proportional to their recidivism rate. And this is what that does. It starts from the same thing and says, okay, I'm going to help Hispanics at a higher rate, and with the goal of reducing this disparity so we can reach equity in recidivism rate. And that's going to, about the same cost as this one. And so this way we kind of provided them with this policy menu, right? Instead of talking about metrics and false discovery rate and false positive rate and parity and all these different things, so what do you care about, right? You have this option, which is most efficient, but leads to increasing disparities. You have this option that's 2% more expensive, but preserves the status quo disparity. You have another one that's about the same, that reduces the disparity and leads to equity. What do you care about? And what do you want? And they, luckily chose the third option, but also it was the right thing to do. And by giving them this menu, it makes it really obvious to them what the policy implications are, rather than kind of get lost in the technical details, which do come later, right? So developing the system and optimizing with that, there's a bunch of stuff that we had to do in the background, but that was in the background. So that's been an example of sort of how to translate from kind of the policy goals and fairness and kind of building these types of systems. And then, a couple of quick examples of things that are currently going on. I think the interesting ones are kind of at the second and the first one is just because we're in Pennsylvania, there's a bunch of stuff we've been doing with the state around COVID type things but then some work in Mexico this is ongoing work on kind of vaccination programs and seeing how do we identify kids not getting vaccinated to do proactive outreach. And then this third one has been really interesting because this is work, because of COVID, a lot more people have been applying for these new social services, for SNAP, for example, people who had never applied before. This is the food stamp program. And one of the things that was coming up was that a lot of these people also needed other services, childcare, mortgage assistance, job assistance, but they just didn't know those things existed. So this work has been to say, somebody who applies for SNAP for the first time, can we look at the application and detect if they are also possibly in need of other services and proactively connect them with those services. So we've been running some trials over the last couple of months with California and Code for America. It runs a system for doing that to see if we can improve how these people get connected. So so I think, summary, basically, I think we've typically sort of, a lot of the work with governments and nonprofits have been the use of data and machine learning and all these things have really been typically to kind of be more efficient. How do we help the most people? And we've been kind of focusing on how do we design them not just to help the most people, but do it in a way it's equitable. And then building that back into sort of thinking about fairness and equity as primary goals and primary metrics, and thinking about them as, again, at the systems level rather than at the machine learning model level, because that's what we really care about. And again, a lot of this work is not really, there are theoretical components, but a lot of it is really, it can't really be done in isolation, right? So it has to be done in collaboration with governments and nonprofits to really test it out, to work with them, to help them, and really do it more effectively. And so just a plug for something we launched about a few months ago. We do a lot of projects right in person, but this was with COVID and a lot of the people asking us how they can help. We launched this a few months back, Solve for Good. That's a volunteer platform that people who are interested in helping with these types of projects and organizations that need help, they post, nonprofits and governments post projects, and then volunteers are kind of working on these types of things. So if any of you are interested, take a look, sign up. It's new, so you're gonna have to be a little bit patient as we figure out how to do this. But we've had a few hundred people join this summer and actively work on projects from around the world. So if anybody's interested. But yeah, and here's my contact. So happy to take questions now, and as well as feel free to email me. And yeah, all the code for all the projects and all the things that I talked about is open source on our GitHub. So if any of that is useful, feel free to take a look. But yeah, happy to take questions.
Thank you, Roy. Thank you so much for that wonderful talk. I think there are some questions in the chat. Hadi, do you want to directly go and ask a question directly?
Sure. Thank you for the talk. Very beautiful talk. My question, I forgot my question, actually. I have to read through it. It's about the bias. So you used the example about students.
Yeah.
And not having sufficient information in order to decide what to do, like what type of interventions you want to do. So this really requires knowing a lot more parameters about the student's lifestyle, ethnicity, et cetera, et cetera. So my question is really about, like, what are the negative ramifications on privacy and confidentiality? Because now you need to ask or elicit more information and more data about them, like what type of, maybe even like data about their parents' job or parents' career, or what type of the family they are in.
Yeah, I mean, the very short answer is nothing I will say about this answer will be new or surprising or deep. Right? I'm going to say the usual thing of, yeah, there are these trade-offs, and as a society we have to figure out how we protect the privacy, but it doesn't mean that we can say, oh, privacy, so I can't help anyone. Right? So it's a societal choice, and this type of support program comes with risks that it could be misused, that if data is kept, right now it's well-meaning, but tomorrow it could be, like that's true for a lot of citizenship type data, right? A lot of these things that it's risky. And I think the question is, how do we set up a system where we can put controls on what actions can be taken on people rather than controls on data? Because controls on data are also really hard to implement. You can say you shouldn't collect this about me, but how do you verify that? But controls on actions are a little bit more, when somebody's sort of doing something to you. I mean, the other piece is, like, we do a lot of these projects are not happening where we're getting, blanket access to all the data, and it's mostly we're working with this organization, so working with a school, and so the data is still owned by the school, in the school. We have a lot of security infrastructure in place. Nothing can be on anybody's laptop. It's all like, and depending on what project, some of them, there's no internet access in that computer, and so a lot of, pretty much everything is under very strict data use agreements. None of it's unfortunate to some level, but I think it's the only way to do it. Is like all the publications I have, I can't make the data public. I can disclose the results, but I think the idea is that if we can set up these types of environments for people to work on in a safe and secure way, then I think it sort of opens up a way to then create versions of it, like the red zone, yellow zone, green zone, where you can make versions of it, but I think, yeah, so go back to my first 3 seconds of nothing I'm going to say will be deep or surprising to you, because I don't, I think it's a societal choice that we have to make with controls in place.
I have a follow-up question, which is kind of related to this. It's about fairness, right? So you mentioned there's lots of incompatibility results and satisfying fairness with this and that. We do a lot of work on fair division or fair resource allocation, those type of work. There are two types of ways that we can think about fairness. Most of the work, at least the theoretical work, is really focused on the fairness of the outcome
That's right.
rather than the fairness of the procedure. So I was wondering if you want to kind of elaborate a little bit on that.
Yeah, no, I was trying to figure out how much to insert that up front because there's enough of, yeah. And I think in most cases, like what in practice, we end up doing both, right? You want to have some procedural fairness thing, but procedural fairness doesn't result in necessarily outcome fairness, but procedural fairness gives you recourse. So I think in practice, it turns out that we need both. And at least for this type, one of the things that would be really nice to have is a notion of, you know, procedural steps that every ML system or every data-driven system that you're building should have to go through. Like, here are the steps you have to go through. It doesn't mean you shouldn't be measuring outcome, because eventually it is going to be about outcomes. But I think we do need, so I'm less kind of, I'm not as polarized on, oh, well, you should only have this and only have that. I think in practice, you're going to need both. But right now there's very few guidelines for people to actually build these types of things. So that's why I focus kind of a little bit more on the outcome, because I know that that's the ultimate goal. But I think the way to get there is you need components of procedural fairness there as well.
Thank you.
There was a question by Aman Gangwani. Aman, do you want to?
Let's see.
I asked it in a private message. I can just say it out loud though.
Yeah.
So yeah, first off, thank you for the talk. It was amazing. You know, when I was a sophomore, I gave a presentation for a class on how some counties are using the recidivism rates to predict what the jail bond should be. And for criminals, and someone brought up the inherent bias of the world. So how do you account for that? So this was a great explanation for that. But my question was more on the police brutality. So the prediction of police brutality events are obviously, you know, super helpful. But one thing I've realized from these seminars is that AI for social good is good, yes, but the models or predictions are only as useful so long as its implementation is robust, which is often seems much harder than generating the actual model, especially in cases like that with police brutality. So how do you enforce these outcomes, or when you were working on that project, or if any of your colleagues were also, how did you enforce the outcomes of these predictions, given the system of, you know, protecting a coworker that we see all too often today in law enforcement?
Yeah, no, I think, and that's the piece that I wish more people, I mean, building a model is both, I don't want to say trivial, but I do want to say trivial. Like if you're a student right now, don't take it literally. It's not trivial. It needs a lot of training, but in the big picture, it's trivial and it has zero impact, right? Because you can do whatever you want on your computer and nothing will happen in the world. And so I think it's what my answer to that is really, when I start a project, I'll mostly only start it if I think that the people I'm working with are likely to actually do something about, take some action. If they're not, then I'm just sort of getting data from them and building a bunch of models and graphs, and nothing is going to change. Now, the tricky thing there is that if you only work with people who are willing to change, then you're sort of helping the people who are willing to change, and nobody else is going to actually change. But in this case, the idea was not to, you know, the ultimate goal is to try to show everybody, other police departments, what they should be doing. But starting with the ones that were willing to change was a way to show that it's actually, this is worth doing, right? Because for them, they had installed these systems, they built them, and then they found that they weren't working, but they didn't have an alternative. So yeah, the way to ensure is there's no way to ensure it, right? There's no legal contractual way for you to say, you will do this thing, otherwise nothing will happen. I think it's more, you find the organizations that actually want to change, just don't know how, and you then help them get there. But you're also sort of helping them figure out how to do it right? So sometimes we'll go in and work with an organization, and as soon as we have something for them, they'll say, oh, let's deploy it. Like, no, hold on. We don't know if it works. We've tested on historical data. We actually need to do an actual field trial. Like, but you said it works. Like, yes, I know it works, but it works on historical data. Well, so you're saying it doesn't work? Like, no, I'm not saying that either. I'm just saying we have some evidence that it works. In order to deploy it, we first need to run this trial. And because right now that nuance doesn't happen, right? Because if they don't work with people like us, the other thing, they'll work with a vendor or a consultant, and they're not going to be that nuanced because they want to sell them something. So I think the maturity right now in these types of things is so low that, a lot of people on the machine learning side don't design experiments and run experiments. And so, again, that's one thing that hopefully is changing, and you guys are, Penn State is much further ahead than a lot of other places where you do have that interaction happening, where CMU, not there yet. Most of our ML students don't know what an experiment is, and so we have to kind of train them on how to get there. But yeah, so I think you're absolutely right that the model, the piece in the middle, is the easiest thing of all. The beginning of convincing them to actually do this thing, and then deploying it and testing it and maintaining it and changing their behavior based on it is orders of magnitude harder. Takes, like, most of these projects I'm talking about, the machine learning stuff was maybe a few months to a year. The rest of it was multiple years, and it's still going on, right? So these have been going on for 2, 3, 4 years.
And then a quick follow-up. So you were talking about like labeling a student in this environment at this time. So how do you, as someone who generates these predictions, ensure that these outcomes aren't taken out of context by people who wish to distort it?
Yeah, so I think that question comes up a lot. And most of it is really, to be honest, mostly hypothetical. Like, oh, what if it gets misused? Like, well, okay, tell me how a school would misuse it. Like, well, a school could fire a student if they don't think they're going to graduate, because that increases their graduation rate. Like, but do schools have mechanisms for firing? You're right that it's possible. Some of these things are easier to misuse, right? So again, if I'm trying to, the example of sort of citizenship questions in census, right? Like that data existed, I can very easily see how it would be misused. But I think other ones are, like, for me, it's partnering with the right organization who believe in the same things as you do, and kind of getting an agreement there is one. So like every project that we worked on, if we had any doubts on kind of the mission and the values of the organization, we would not work with them. The second is to then put some of these things contractually, which is, this can only be used for these purposes. It's not about the data, it's not about the models, it's about the actions you can take on people. The third one that we've done is transparency. So in all the contracts that we do with these organizations, we will say we will publicly disclose what we have done. We're not gonna, keep anything, so that the entire world knows what we're doing. So in case things happen where they misuse it, the media knows, and the reporters know, and everybody knows that this is what they have been doing, this is what they have access to. None of that guarantees that it can't be misused. It's just, it reduces the chances. And so I think it's like, I would do all three, right? Is select the people and have these conversations up front, put in legal and contractual things in place, and then be transparent about what's happening. And I think that's at least our strategy in these projects.
Okay, thank you.
Sure. There's time for one final question, and then we can move to the social gathering. So Bru Zong is asking, while you've done so many excellent projects, what are some social science approaches that you think you've needed the most in your research?
Yeah, I think from our side, it's been, it's been, a lot of it has been really more around causal inference things, in whether it's sort of through experimental work or through observational work, because again, a lot of these cases do require us. Some of them are pure prediction tasks, but some of them are causal inference tasks. And eventually there are, I think the lead poisoning is kind of one of the few examples where if I can predict it and remove the lead, then I don't need to figure out the causal mechanics of, how, but in most of the cases, I'm actually trying to do more causal inference. So that's been the kind of the most But I think the other piece that's been really good is in all of these projects, the teams that have been doing these projects, whether it's students or postdocs or researchers, have been a mixture of computer science, statistics, social sciences. And I think for me, it's painful in the beginning, which I'm sure you guys have felt that pain of putting those people together because the language is different, the backgrounds are different. But it's good in the long term where they learn sort of the value of the other disciplines when, you know, each discipline thinks they are self-sufficient to solve any of world's problems and none of them are. So I think that's been the other benefit, is just exposing people to these things as, you know, like machine learning doesn't have the monopoly on data analysis, or econ doesn't rule the, well, it does rule the world, but hopefully not for long. So that's been the other piece, is just having people get exposed and then eventually using a broader set of tools. And that's how we sort of position these things. You know, we've got all these different tools to do things with data. And we need all of them in order to solve these problems. And, you know, who cares if it comes from operations research or stats or machine learning or social sciences. But that's unfortunately now how the universities are designed.
You know, I just want to add up, like, thank you very much. And to talk about this, we do actually a lot of research regarding equality or disparity, but, you know, really did not think too much about efficiency, and equality could end up to have some trade-off. So you have to find a good balance about this. That's got so much inspired by this kind of research. And, you know, and we talk a lot about the interdisciplinary research, but, you know, really good ones, very hard to come up with. So that's why I asked this question.
Yeah,
here, you know?
No, it takes so much longer, right? And it's so hard to do if you're really going all the way, and it's slower. Like right now, I'm teaching a class that's joint between half the students are from the machine learning department, half the students from public policy, and it's the clash is but yeah, I think that's the hope, is that more people do these types of things. But we have to also create the incentives for them to do this. And that's, I think, the bigger challenge.
That's right. You know, this semester I'm teaching a PhD class, and, you know, several come from IST, you know, other, you know, from other social science departments there. And we enjoy it. You know, the conversation is wonderful. Yeah. Thank you.
Thank you, everyone. We are out of time. After this, as I mentioned in the chat, there's a short, since we are out of time, it's going to be shorter than usual gathering on Gatherer Town. The link has been provided in the chat. Thank you, Dr. Ghani, for coming in, and wonderful talk.